So let's begin our next main chapter here in chapter 3, in which we're still going to be calculating and using derivatives. But in this case, we're going to be utilizing in 3.1 here, the first derivative to help us graph or visualize the curvature of a function. And this is known as, and what we're going to be doing here first is using the first derivative to calculate the optimal points of a function. This process is known as optimization. Right? And what optimization means, it means the maximum and the minimum point or values of a function f of x. All right, so in 3.1, we're going to be looking at application of first derivatives to help us optimize a function to find its highest point or lowest point around our neighboring set of order pairs. Now, how are we going to do this? By looking at the behavior of our function based on its slope. Right? Recall, f prime, the first derivative, tells us, calculates the slope of a function. Right? It calculates the rate of change of a function. So if our first derivative is positive, that means the slope of our function is positive. And if the slope of our function is positive, that means that function is increasing, right? If the first derivative is positive, then our original function f is increasing at that point. But if our first derivative is negative, that means the slope is negative, meaning the rate of change is going down for our function. Meaning at that point, our function of x is starting to decrease. Okay, and we can visualize this relationship between the first derivative and our function through some curvatures here. Say, for example, and it's actually something we saw a bit in the last chapter as well. All right, suppose a function has this type of curvature. All right, suppose a function has this type of curve. That is pretty nice. All right, so here we have f of x. And we see at this point, if we pick any point along this curve on f of x here, if we were to calculate its slope, if we were to calculate the first derivative at that point, or in other words, find the slope of the tangent line at any of these points, that slope will be a positive value, right? F prime will be greater than 0. Put a different color, right? F prime will be greater than 0, indicating that our function f here is increasing. Okay, but if the curve of function were to have this behavior here, then in that case, our function is decreasing, right? Our function is coming down towards negative infinity. All right, so in this case, f of x is decreasing. Its values are getting, its values of along y are getting smaller as x is increasing, which means then if y is decreasing along with x, that means at any point here, we're going to have a negative slope. So our first derivative, if valued at any point along this type of curve, will be negative. Okay. Or, again, it's pretty similar to something we saw in section, I'm trying to recall, may have been 2.5, where I did this little curve, where I drew these little curves here. Okay. Now, if our function also looks like this here, if it has this type of curve, then again, the values of our function of x here, the values of f of x along the y-axis are getting smaller as we move from left to right. Meaning once again, f of x is decreasing, which means once again, the first derivative evaluated at any point along this curve, the first derivative will still be negative. All right, and then lastly, why didn't I draw the line? All right, and then lastly here, if our function has this type of curvature, then once again, the function is increasing, because as we move from left to right, let me redraw that curve, because as we move from left to right here, the values of this function f of x are increasing as we go, as x is also increasing. So once again, our function is increasing, which means then if we evaluate the first derivative, at any point along this type of curve, the first derivative will be positive because the slope will be positive. Okay, so notice that the first derivative can help us indicate whether our function is increasing or whether the function is decreasing based on the values that we obtain from the first derivative, based on the values of the slope, based on the rate of change of our function. Again, like we saw in chapter 2, the first derivative tells us the behavior of the original function, the rate of change of it. Okay. And what we want to do here is we're going to be using this first derivative to help us identify these optimal points along a curve. Meaning we want to use the first derivative to find the maximum and minimum values of this original function. We want to use the first derivative to find the highest peak or the lowest peak of a curve. All right, in other words, identify where the function changes its behavior, where it changes direction, whether it goes from positive to negative or negative to positive. Identifying that change in behavior will help us identify its optimal points. Okay? And these points at which it changes behavior and which it could possibly change direction, those are known as the critical points of a function. Also referred to as the critical numbers. I tend to say critical numbers, so I'll use that phrase more often. The critical numbers / points. Okay? The critical points here, the critical numbers, are the x-coordinates at which the function, our function f of x, is going to have a slope of 0. Again, look at this point here. Look at these two. Look at these two graphs. If we were to connect them together, before the function changes direction, at some point the slope of that function has to be 0, right? If we want to go from positive slope to negative slope, if we're going to go from positive to negative, at some point that slope has to become 0. And that point where it becomes 0, that is known as the critical number of that function. All right, so the critical numbers will be the x-coordinates, and I'm going to emphasize that the x-coordinates at which the slope of our function is either 0 or even undefined. Okay, where the slope is undefined, that also indicates a critical number, a critical point of our function of x. All right, and we're going to be using these critical numbers, these points in which the slope becomes 0, to help us identify what's known as relative extremas. And we have two types of relative extremas. We have a relative maximum and a relative minimum. The relative maximum point, it is the point of the function of x. It is a point of our function of x that is at least as high as its neighboring points, at least as high as its neighboring points. In other words, it is the highest peak of the function relative to the other points that surround it. Okay, and then we want to try to see if we can identify a relative minimum point. And the relative minimum point of a function That's going to be the point that is at least as low, or at most as low as its neighboring points. In other words, there's the lowest peak, the lowest valley of a function relative to the other points. Okay, in other words, these two relative extrema are going to indicate where the function changes direction, either from positive to negative in terms of the slope, or from negative to positive in terms of the slope. In other words, it's the points in which a function is going to either start going from increasing values to decreasing values, or from decreasing values to increasing values. Okay, let me draw another graph here. Just get kind of visualize where we will find a relative max or min. All right, so let me do a graph here. I want to make sure I have enough room. That should be good enough. Okay, so suppose we have a function with this type of curvature. Suppose we have a function with this type of graph. Oh, it doesn't smooth it all out. That's lame. All right. So here we have a function that from the beginning is increasing, but then changes and reaches a high point here before it starts to fall down. So now it's starting to decrease, but then reaches a low point, and then once again changes direction and starts to increase again. These 2 points here, at which it changes direction, at which our curvature for graph changes directions, those are indicating the critical points, the critical numbers of our function. And let me call them, say, A and B for now. All right, so here we have A, and here we have B. And A and B are representing our critical numbers. Okay, the points in which the slope of our function zeroes out. All right, so zeroes out over here, and it zeroes out over there. Oops, in other words, where the slope of the tangent line at that point is 0. And in this case here, in this first critical point, since our function was increasing and reaches high point, and then before it started to come back down, then this first critical number is representing the point in which our function reaches a relative maximum. So at this point, we're going to have a relative maximum. In other words, here we have reached a high peak in our function. Whereas for the second critical number, since in this case our function is decreasing, is coming down, and then reaches a low peak before it changes direction, starts to come back up, then this second critical number at B, that's representing the point in which our function, in which the values of our function reaches a relative minimum. So the y coordinate at this point is going to represent the relative minimum of our function. And we have reached a low peak, in other words. I'll say min for minimum. Okay. So at these 2 points where the slope is 0, I'll make that note here. So here the slope f prime will be 0, and at this critical number, the slope will also be 0. And in this case, both critical numbers have identified a relative extrema, a max because we changed the direction from positive to negative, and then a minimum because we changed the direction from negative to positive here in terms of the slope. Okay, again, a critical number can be a point of our function in which the slope is 0 or even undefined. With an example where it could be undefined. Let's see. Oops, too large. All right, so undefined slopes tend to occur when we either have asymptotes or we have sharp turns in our function. So suppose our graph looks like this. All right, so here once again, we have two critical numbers, and which slope, in this case, however, will be undefined at this point here, at this high peak here, and at this low peak here. Okay, so once again, here we're gonna have relative maximum, here we're gonna have relative minimum, but at these 2 points here, the slope is undefined. All right, f prime, or can't really draw a critical tangent line like that. So at these 2 points, f prime is undefined, does not exist. Can't really draw a tangent line at sharp turns. All right, but even if the slope is undefined, those two critical numbers can still indicate if whether we have relative max or min at those sharp turns. All right, so more definitions here. So again, our function of x is said to have a relative extrema or relative maximum value at some point C if our function evaluated at that point for C, again, is at least greater or equal to any other point in that function near C, for all values of x near C. Again, this is the highest point of this function here at this point, as this first critical number, compared to its neighboring values. And an f of x is said to have a relative minimum value at some critical point represented by C if our function evaluated at the critical number is at most less than or equal to the values of a function of x for all other points near this critical number. Okay. And these critical numbers, let me just note here. These critical numbers represented by C of a function f of x. Again, if it is an x value, an x coordinate, a critical number is not the entire point. The critical number is just the x coordinate at that point. All right. It is an x value or x coordinate in the domain of our function. Okay. At which, again, if we were to evaluate this critical number in our first derivative, our first derivative will come out to be 0. If we evaluate this point B here along x, if we plug in B into our first derivative, the first derivative will be 0 because again, what does the first derivative tells us? It tells us the value of our slope. And if it's flat line, then at that point, the slope is 0. Whereas in this case, if we were to plug in A and B into the first derivative, the first derivative will be undefined. All right. So our critical number is the point that if we plug in this critical number into our first derivative at this point x will either be 0 or undefined. Actually, let me call this C instead of x. F as critical number, it values this first derivative, it will be 0 or it will be undefined. Okay. So let's look at the steps here and how we go about finding these critical numbers to help us identify any potential relative max or min of our function. Okay. Oops. There we go. All right. So to find these critical numbers in which our first derivative will be either 0 or undefined at those points, to find the critical numbers of a function of x, we do the following 3-step process. First step, we have to know the first derivative. So first step, find f prime. We have to identify the first derivative in order to find these critical numbers. Now, after we find the first derivative, how do we calculate or find these critical values? Well, again, the critical numbers are the points of x in which if we evaluate our first derivative at these critical numbers, it will either be 0 or undefined. Okay, meaning these critical numbers are the zeros of the first derivative. And how do we solve for the zeros of a function? Recall for algebra, how do we solve for the zeros of a function? By setting that function equal to 0 and solving for x. So the second step, set the first derivative equal to 0 and solve for x. And that will give us our critical numbers. Okay. And the third step deals with finding the relative max or min. To find the relative extremas of a function, we run what's known as the first derivative test, which I'll talk about in just a little bit. All right, so after we find our critical numbers, then we run what's known as the first derivative test to find the relative extrema of our function of x, of the original function of x. Again, we're using the first derivative to identify these relative values, these relative extrema values of the original function. Now we're using the first derivative to identify the behavior of our original function. All right. Again, let's see how we can find these relative extremas once we obtain our critical numbers from the second step. Again, we have the relative maximum points f of c. All right, our critical number, evaluate our original function, will give us a relative maximum if the following is true. To identify relative maximum based on critical numbers, relative maximum occurs when the sign of our slope, f prime of x, changes from positive to negative. Meaning our function, in other words, when the slope changes from positive to negative, that is indicating that at first, our original function f of x is increasing, then zeroes out, it reaches a flat line, it reaches a peak, and then comes down. Again, look at the example that we have here. At any point before it reaches this high point, at any point, if we evaluate any point here in the first derivative will be positive. All right, because since our function is increasing, that means we have a positive slope at any point along this curve. But then it reaches its maximum point. At that maximum point, the slope zeroes out, and then the slope becomes negative, indicating the function is started to decrease. So when the slope changes from positive to negative, then that means at that point before it changes direction, we have reached a relative maximum. Okay, so again, when the slope changes from positive to negative, it goes from positive, 0, or undefined, and then negative, then at this point, we have reached a relative max. I'll say rel max, relative maximum. Okay. But if it's the other way around, then we're going to have a relative minimum. All right. We have a relative minimum at our critical points, evaluating our original function, when the sign of our slope, based on the first derivative, changes from negative to positive. Okay. We Because in this case, that is indicating that before I reached that critical number, our function was decreasing. So our function is decreasing, meaning it has a negative slope at any point along that type of curve. And then it zeroes out, slope becomes 0. And then the slope becomes positive, indicating that our function is now started to increase. So here we went from negative, 0 or undefined, and then positive. And at that point where we're zeroed out, we reached a relative minimum. Okay, so if the first derivative, if the slope of our function changes from negative to positive, we have reached then at that critical point where it becomes 0, where we're zeroed out, we have reached a relative minimum. Okay. And we use what's known as the first derivative test to help us indicate these changes in direction. All right, so let's look at the first derivative test. All right, so if a function f of x has a critical number represented by c, then f has one of the following two. It either has a relative maximum if the first derivative is positive just before hitting that critical number, and then becomes negative after passing that critical number, right after passing that critical number. Okay. Or it's going to have a relative minimum if the slope is negative before hitting that critical point, and then becomes positive right after it. All right. And how we do this first derivative test is we're going to be using a number line to indicate these change in directions based around the critical numbers that we have found. All right. So for the next part of this section here, 3.1, for the next video part, it's going to be doing several examples of finding these critical numbers and determining whether these critical points, do we have relative max or relative minimum, or neither. If there's no change in the sign of the slope, if there's no change in the direction, then in that case, we have no relative min or max at that point. What we have instead is what's known as the saddle point. All right, so we'll do a few examples of finding these relative extremes of a function in the next part for this section.